Welcome to chapter 3. So I did cover 3.1 in my morning class. And so now for the afternoon class, we are now going to look at 3.2. And videos of both of those will be posted on our Canvas site, hopefully by the end of today for review. Or if you want to see 3.1, because I didn't go over that with you directly, that should be there by this evening. So in chapter 1, we got an introduction to statistics, and that involved a lot of vocabulary and just trying to wrap our minds around the idea of collecting data from a sample of a population so that we could look at the data from our sample and try to make inferences or draw conclusions about the overall population. Just the idea of that and how to do samples and things like that. Then in chapter 2, we started to look at what to do with the data from our sample, how to organize it, how to display it. And we looked at creating frequency distribution tables or histograms or dot plots, things like that, so that we could look over and organize and understand even the shape of the distribution of the data values that we collected from our sample. So in chapter 3, we are now going to begin the idea of analysis. And so what I mean is, now that we have these data values, what type of calculations do we do in order to then draw conclusions or understand the data better, other than just looking at a picture of what the data values are when organized nicely? So the title is Describing, Exploring, and Comparing Data. So there are 3 sections in this chapter. The first section is about measures of center. And so that was discussed in the earlier video. Measures of center will be things like the mean value, which is like the average, but the mathematical idea of an average, the mean value, the median, which is like the middle value, the mode, which is like the value that occurs most frequently. And there's other terms that were defined for measures of center in 3.1. So in 3.2, instead of looking at measures of center, we're going to look at measures of variation. And so measures of center was ways to try to understand kind of where the middle of the data is. Measures of variation will be ways to give us a sense of how much the data values varied from one another. If you think about a distribution of data like we did in chapter 2 with a histogram or things like that, then variation is kind of about how far apart the data is spread. And there's more than one way to think about that. You could just think about how low the lowest value is compared to how high the highest value is. What's the spread from the very bottom to the very top, or vice versa. That would be one simple way of thinking about the variation in the data. And we'll talk about that. But also you can think about just how far the data values themselves are spread apart from each other. And so we need to think about these ideas and give definitions and look at the properties of the calculations that we're going to do to understand measures of variations of the data. That's the idea. So how does the key concept describe this? Variation is the single most important topic in statistics. So that's a bold statement. So basically they're saying, if you ever wanted to open your eyes and pay attention, now's the time with this discussion right now, because this is the most important thing in the semester. So that's an interesting way to start their key concept, and I honestly agree. So that just means take note, and if you ever wanted to spend extra time trying to understand and think about a concept, variation is one of the best ones in statistics to really spend some extra time on. So it says, because of that, this is the single most important section in the book. This section represents 3 important measures of variation: range, standard deviation, and variance. Now, those words are in bold font or emboldened, which means that they are going to define those in the coming slides or coming discussion. So they don't expect when they say those now that you know what they mean. But nonetheless, they want to draw your attention and say, these are the things we're going to talk about. They're going to say what they're going to say, then they're going to say it, then they're going to say what they said. These statistics are numbers, but our focus is not just computing these numbers, but developing the ability to interpret and understand them. Now, that's great that they say that, but as you're going to see in the slides in front of us, and if you look through the book, you might not feel that way when you're looking through it, because even though they're not going to just focus on computing, they're going to spend a lot of time talking about how they do the computations. And I'm going to try to de-emphasize that even more than they're saying now, because we are going to rely on technology to do those calculations for us. I'm going to basically skip through very quickly slides that are showing us complicated formulas and lots of different notation. Now, that doesn't mean that I want you to never look at those at all, because you do need to have at least an understanding of the notation so that when they reference things using that notation, you know what they're talking about. But our shared time together is best spent immediately thinking about the harder part of understanding the material, which is what they're saying is the interpreting and understanding of these statistical numbers that we get. And so that can best be done by thinking of an example, understanding and talking about how that example might illustrate some part of what we're trying to understand here, and having some back and forth about that, looking at units, doing what's called unit analysis, like what would be the units of that number? Is that feet? Is that square feet? Is that minutes? What is that? So that you can try to wrap your mind around the reality and the interpretation of the numerical results that you get in these statistics. Okay, so having said that, let's proceed. Now, because these statistics are numbers, they're right off, we're going to be working with numbers. They're starting off by talking about a round off rule for measures of variation. And so this is kind of nice, nice rule of thumb to follow when doing calculations. However, I will point out for our practical purposes that as we're doing problems in my stat lab, that when a number needs to be rounded off, they tell you in the box where you enter the number exactly where to round off the number. So happily, you don't have to worry that there's some criteria you're going to forget about when you were supposed to round to where, in which circumstances. Because if you simply just round off where the problem tells you to round off, you'll be safe. But in general, they'll say you go 1 decimal place further than what was present in the data is a good round off rule of measure, specifically for variation, So if the data values were rounded off to the 10th place, then you might be wanting to round off to the 100th place when you do your calculations. Okay, now they're going to start defining measures of variation. And the first one they define is the first one that I was discussing with my little example, the range. The range of a set of data values is the difference between the max and the min, the maximum value and the minimum value. All right, so to make a difference and to have a max and a min, just to be clear, the data has to be numerical. So we're talking about numerical data. You can't have a difference in colors, right? So not categorical data. And so in the example I gave in the beginning, how far apart the data is from smallest to biggest as a way of measuring the variance in the data, that's called the range. Specifically, the value difference between how big the biggest value was and how small the smallest value was is the range. Now let's think about this as a specific example right out the gate, so that we can even imagine what the units of the range would be. So let's say my data values are heights of students at DVC, and I measured that in inches, like 65 inches, 66 inches, things like that. Well, then I'd have some smallest height measurement and some largest height measurement. Let's just make these up and say that it was 5 feet was the smallest person in my sample. That would be 60 inches. And let's say 6 feet was the tallest person in my sample, that would be 72 inches. So if I subtracted 60 inches from 72 inches, I would get a difference of 12, and the units would be inches. Inches minus inches is inches. So there would be a 12-inch range from the smallest to biggest height measurement of my sample. Questions, comments, discussions about the idea of the range of a data set? So how about this? Just take a brief second in your mind to imagine a data set of any kind that you want and come up with a number and the units that might make sense as the range for your data set. And if you're willing to share it with us, with the class, that's great. But try to think of one, whether you're going to share it or not, just so that you're trying to make this discussion active in your mind and understand these concepts. Think of a data set and what a possible range value might be. Anybody want to offer one up?
I think I might have one.
Okay.
Could it be the grades of an exam? So a range of the data set could be like 95 is the max, 65 is the minimum, and then numbers and ranges in between those.
Great. So if grades are the number that you got as opposed to like an A, a B, or a C, so you might want to say the scores of exams, even though those could be translated to grades. Just trying to think about the words. I think grades are usually the letter, and you can't take a difference of letters, and I can't have a range of grades as defined here. But if we said the scores on exams, then you could do that. And then what would be an example of the number you would get along with the units in your example?
Do you mean like the numbers that would be the outcome from all the scores?
We can look at those if that's helpful, but in the end, the range is a number. So could you give an example of a range that might happen in the circumstance you were describing and in the data set that you were describing?
So if the maximum score was a 97 and the minimum was 67, then the range would be 30.
And what would be the units of that? 30 what's?
Points.
Points, I think, is good. You
Yeah.
could say test points or quiz points, but I think we usually say points, right? And I really think this goes a long way to really help us put the math to the street, to try to think about units of all measurements that are measuring something in the real world. That's a great example. Anyone else want to share one?
I do. Distance, it could be distance, like the minimum could be 5 kilometers and the maximum could be 30 kilometers and the range could be 25 kilometers.
Absolutely correct. Now, could we fill this out a little bit, just helping our imagination? What's being measured?
The kilometers that a runner is, I don't know, running.
Nice. You're talking 30 kilometers marathon distance. That's
marathon.
good.
Yeah.
Yeah, that's exactly a great example. So yeah, it's really good to remind ourselves also, as we are thinking of examples of data, the data comes from observations and measurements in the real world. So even when you're making things up, a little bit more of the picture that you can fill out that way, because then you could say what the range meant in that context. But that's a great example. So that you could say the range of distances run by my sample of people or joggers or marathoners or whatever was 25 kilometers. And what that means is that the variance between the shortest distance run and the longest distance run, the variance, the spread in the data was 25 kilometers. There may have been no person who ran 25 kilometers, but the gap between the biggest distance run and the shortest distance run is 25 kilometers. All right, lots to do. Let's move on. So as they're discussing these statistics in chapter 3, and in 3.1, you'll see this in place already. And I did discuss this more when I was talking about 3.1. they start to, when they introduce a statistic, they start to talk about the properties of the statistic so that we can compare and contrast the different types of statistical measurements. And so when talking about range, they're going to continue the process of thinking about what properties does this have. And so one of the things that they talk about is being resistant. And they define that in 3.1, but the basic idea is a measurement calculation like range or some other statistic is resistant if a few extreme values in the data set, extreme outliers as we loosely define in chapter 2, if a few of those do not have a strong impact on the value of your calculation. And so when they do not have a strong impact on the value of your calculation, you say your calculation is resistant, meaning it's resistance to being influenced from a few outliers. Now they're using this property discussion and applying it to range. Now it says the range uses only the maximum and minimum data values. So it's very sensitive to extreme values. If there was some extreme high value, well, that would immediately be one of the only two numbers you used in your range calculation. And so that would change your range completely. So because it is not resistant to that, then they say the range as a calculation is not resistant, not resistant. Because the range uses only the max and the min values, it does not take every value into account, and therefore does not truly reflect the variation among all of the data values. So when we're looking at calculations, one of the things we want to think about is whether the number that you're getting is some reflection of all the data values in the set. And that's more easily verifiable if all the data values in the set are used to do that calculation, to come up with that number. Because if some of the data values are ignored, then it may not reflect that part of the data in some way. And in this case, almost all the data values are ignored. You only take the smallest and biggest in order to determine the range. This might make more sense as we talk about some of our other measures of variance and whether or not they take all the data values into account or not. So let's pause here. Any questions or comments or discussion about the idea of range at this point? All right, we'll keep moving. And they do give us an example. Find the range of these Verizon data speeds, and they give you in units. And that little thing there, they used this as an example earlier. I think they might have spelled that out. That's megabits per second. It's a unit of measurement, like miles per hour. So then they give us, there's like 5 of them here. So the range, you'd have to identify what's the biggest value. That's 55.6. What's the smallest value? That's 20 or 14.1. And then they take the difference to get the range. And notice when the range is written here, they're also using the units, megabits per second. All right, now our number one most important statistic in the number one most important section for the semester, standard deviation. So standard deviation of a sample, of a set of values from a sample, denoted by the letter little s, is a measure of how much data values deviate away from the mean. The mean was defined in 3.1. So the mean is like the arithmetic average value. If you have numerical data and you add them up and divide by how many there you are, you get the mean value. And it's sort of an idea of saying what the middle is. So if there's this middle sort of central position, this mean value, the question is, are all of the data values that gave you that sort of balancing value in the middle, are they all kind of close to it, or are they all spread far apart from it, or somewhere in between? So standard deviation is a calculation that you will not want to do by hand. It's pretty elaborate, and they're going to show you some formulas that we're basically going to ignore because we're going to use StatCrunch, or you're welcome to use some other statistical software to do the calculation for us. But nonetheless, when we do it, you're going to get a number. And that number is somehow measuring how far apart the data values are distributed from their middle, from their own middle. Whatever their middle is, how far are they spread? Did you get that middle by having lots of data way far on either side, or are they all kind of lumped up in the middle? And you may recall from our earlier graphical work, we talked about sort of a normal distribution. And when you had this big lump in the middle, the idea was in the middle was something like the mean, and that more data often with a normal distribution will lump up in the middle near the mean. And so what you can imagine graphically is that as the data had a higher standard deviation and was spread more or deviated away farther from the mean, that curve of distribution would spread out wider, and the data values would move more away from the middle. And that would cause the value that you get from your crazy calculation for standard deviation to be higher. We're going to be able to understand this more as we work with this, but that's the initial idea. So they're writing away, giving some notation. Little s is used for the standard deviation from a sample that is taken. And again, when we take information from a sample, we're using that to then imagine that we could say then something about the population value. When I was talking about the average or mean height of students at DVC, it was because I would look at my mean of my sample to then talk about the mean value of the overall population of all students. And that they're going to use different symbols from those all along the way. So the little s is for the standard deviation of a sample, and this Greek symbol called a sigma is for the population standard deviation, meaning for my entire population, how much are the values of the population deviating away from the mean value of the population? It's very possible for some of you that we've reached the point now where we have enough accumulated statistics vocabulary that some of the sentence I'm saying make no sense to you whatsoever. That there's a few words you're not used to using, and I say something and you're like, I don't know what he's talking about. That's natural. You want to fight that tendency, and the way to fight it is, if you're really feeling lost, try to be engaged with this conversation. Try not to just listen passively. Speak up and say, Mr. Willett, can you say that again? Or Mr. Willett, I hear what you're saying, but can you give an example because it's really unclear? I think all of you are potentially vulnerable to this happening, and with your help, I can try to alleviate some of that, but I can only do that with your help by responding to points at which you're feeling overwhelmed and trying to elaborate or explain things better. Having said that, any questions about this definition of standard deviation before we move on to some examples?
I had a question about the sign that looks like a little O, the sigma. So I've seen that before, but does this only correlate to standard deviation?
In statistics, yes.
Okay, all right.
It's just a Greek letter, so it can be used just as a variable in other math classes or to represent like sigma, phi, delta symbols for a fraternity house or something.
Oh, yeah.
To use Greek letters. But yes, in the convention in statistics will be to use standard sort of, I guess, Roman alphabet, like our normal letters for things that were taken from the sample, and then these funny looking Greek letters for things that are talking about the entire population.
Okay, all right. That's fair enough.
They kind of stick to that through the course.
Yeah. All right, cool.
Other questions while we're here? All right, standard deviation, number one most important topic. As I promised, there's the formula for standard deviation, and here's how much I think we should talk about it. that much. So because I don't think there's any value other than to scare and confuse students, and I'm never going to ask any of you to use those formulas, I'm going by them quickly. However, as we were just discussing, as we're thinking about what these statistics mean, we look at the properties. So we looked at properties of range, and now we're going to look at the properties of standard deviation. So the first one says the standard deviation is a measure of how much data values deviate away from the mean. That's not a property, it's just the definition. The value of the standard deviation S is never negative. It is 0 only when all of the data values are exactly the same number. So as soon as any numbers move away from each other, so that there's a mean value in the middle and there's any gap between them, then you will start to accumulate a value for your standard deviation. If all of your data values are all 5, then the average of, or the mean is 5, and they don't deviate it from at all, so the value is 0. So as you're thinking about how far away data values are from the mean, you can think of that like distance. How far are you away? Well, are you above or below? Well, we don't care. We just care how far away you are. And when you're thinking about distance between things, that also makes sense to never be a negative number. I can't be -2 feet away from something. So for that same reason, standard deviation as a result never comes out to be 0. It's only 0 when there's no deviation, and it grows from 0 in a positive direction as data moves away from each other, creating a mean value in the middle somewhere and some space between some of the values and the mean. So that's an important concept to understand about the standard deviation number itself. Larger values of S indicate greater amounts of variation. So it's a measurement of variation. The more data is spread, the bigger the number. The less data is spread, the smaller the number. The standard deviation S can increase dramatically with 1 or more outliers. So you could look at the formula to understand why that's the case, but let's just trust it. And as we work with it, you'll see this occur. The standard deviation can increase dramatically with 1 or more outliers, meaning extreme values. So using the language that we had about range, that would mean that the standard deviation is not resistant. It's not resistant because it is easily influenced by a few outliers. Now they're talking about the units. The units of the standard deviation S, such as minutes, feet, and pounds, are the same as the units of the original data values. So in that way, it's kind of like range. With range, we just took the difference between 2 data values. So if I have feet minus feet, I get some difference in feet. The same is true for the standard deviation. It's not as simple as a difference. The formula is much more complicated than that. But in the end, you end up with the same units as the data itself. Then it finally says a new bold description, meaning they kind of need to define this. The sample standard deviation S is a biased estimator of the population's standard deviation, sigma, which means that the values of the sample standard deviation do not center around the value of sigma. That's a concept that has to be explored more. Basically, the earlier measurements are unbiased. Standard deviation is an example of a biased. And we have to look at that and look at a lot more graphs to understand that. So don't feel that has to make perfect sense right out the gate, because that's just not realistic. But it can come to make sense through our studies. Okay, so bottom line at the top here, standard deviation is not resistant, meaning that it is easily influenced by outliers. And the units that you get from a standard deviation calculation will be the same as the units from the data itself. So now they're going to give us an example of calculating standard deviation. They literally have a data set here with only 5 values and the formula isn't even written out what they did because it's too hard to do yourself. So we will just almost never do it ourselves. But what I will point out about this example is that the data was in megabits per second. And after they did this normal number crunching, they got a number measurement that was in data per megabits per second as well, the same units as the data itself.
I had a question on, I think it was like 2 slides back when you're talking about standard deviation, how it can never be negative unless the values are exactly the same.
Yes.
So what would be an example of it being negative actually?
No, it can't be.
Oh,
It says it's never negative. So I can't give you an example where it's negative.
only when the data values are exactly the same, right?
No, then that's when you get the 0.
Oh, okay. Oh, so never, ever. Okay, got it.
Yeah. So how much variance is there? The minimum amount of variance, I'm sorry, the minimum amount of variation that the standard deviation can measure is 0.
Got it. That's the lowest it could go.
It's like, how far apart are they? 0, meaning not at all. I can't be negative far apart.
Yeah.
Does that make sense?
Mhm.
Good question. Other questions? Feel free to chime in. I appreciate them. Calculating standard deviation using a shortcut formula. We're not going to use any formulas. Go away. Don't bother me. So range rule of thumb. So this is a way to kind of ballpark the idea of standard deviation. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. The vast majority, such as 95% of sample values, will often typically lie within 2 standard deviations of the mean. Let's see what their next slide is about that. Yeah, so they're going to try to quantify this with a formula. Before they do that, let me try to explain it with something more simple, and then we can look at their fancy way to try to tell you what they just told you. All right, so what does that mean? So let's say I was measuring the height of students at DVC, and I ended up with in inches, and I ended up with a mean value of, I don't know, let's say 5'6". That's probably too low, but we'll say 5'8". So let's see, 5 feet is 60 inches. So I'm going to say that we ended up with a mean, I'm just drawing here, of 68 inches. So then what does the standard deviation measure? It measures how far my sample heights of students varied from 68 inches. I don't think every student, especially if I had like 100 of them, was exactly 5'8". I had some short people, I had some tall people, but the mean value came out to be 68 inches. So let's say that the standard deviation ended up being 4 inches. So I'm giving it a unit that matches the unit of what I'm measuring. So these are heights. So what does that 4 inches mean? What is that standard deviation is 4 inches with my sample student heights at DVC? What the heck does that mean? The rule of thumb would be that of my 100 people in my sample, the vast majority, like 95 out of 100 of the values in my sample lied within 2 standard deviations of the mean. So how am I within 2 standard deviations? That means no more than 2 standard deviations above and no less than 2 standard deviations below. That's within 2 standard deviations, meaning I couldn't go above or below more than 2 standard deviations to lie within 2 standard deviations of the mean. So what does that look like? If I'm thinking about a range of values and I'm putting my 68 in the middle, then if I add 1 standard deviation, then I would get up to 68 plus 4, which would be 72 inches, which would be 6 feet, because 5'8" plus 4 is 5'12" or 6 feet. So that would be 1 standard deviation of 4 inches larger than the mean value of 68 inches. If I then go another standard deviation up, plus another standard deviation, then I would get up to 76 inches. So 76 inches is 2-inch distances, two standard deviations above the mean. 4 inches once, 4 inches twice, total of 8 inches above the mean. So that's, if I go bigger than 76 inches, then I'm more than 2 standard deviations above the mean. And similarly, if I imagine going below the mean 2 standard deviations, that would get me down to 60 inches. So 60 inches is 2 standard deviations below the mean. And so that means if I think about all my sample values that were between 60 and 76 inches, all the values in that range, those are the values that lie within 2 standard deviations of the mean. And the rule of thumb is that 95% of the heights in my sample would be between 60 inches and 76 inches. How do you guys feel about that?
I get that. I get that.
That makes sense to me.
I think this is hard, and I'm glad some people are chiming in and able to follow it. This is the key concept for standard deviation. So if you're feeling confused and you're willing to ask a question, that would be great. Now, I've drawn my little illustration so that I could sort of explain my way through it. But let's go ahead and look at their much prettier visualization of this, and then we'll maybe look at some more examples. So here is a visual impression of the range rule of thumb. So that means they're going to say something is significantly low if the values are, so again, here's those Greek letters. I think the U looking thing was in 3.1, even though I don't remember that coming up on the slides, but maybe it did. So this is the population mean or average value. And this is the new symbol we just looked at for the population standard deviation. So a range rule of thumb, and now you can extend this to the whole population or for a sample, is that values are significantly low if they are less than 2 standard deviations below the mean, less or at that level or lower. And so they're showing that here because they're saying, look, over here, these are significantly low. There's the mean in the middle. And if we go below the mean up to 2 standard deviations down, then all of a sudden you're going into significantly low territory. So to apply that language in my sample up here, I would say that heights that I measured of students were significantly low if the students were 60 inches or shorter. And similarly, they're significantly high if they were 76 inches or taller.
Mr. Willett?
Yeah.
Do we use, in your example, do we use S because you only measured 100 kids instead of the entire population of DVC?
Exactly. Exactly. So if I was somehow had access to all of the heights of all students at DVC, then I could come up with the standard deviation of everybody, which would use that little sigma symbol. And I could come up with the mean value for everybody, which would use that little U referred to as a mu symbol. But it's the exact same rule of thumb. And I would be talking about everybody instead of in my sample. Now, in my sample, I can confirm this. But the range rule of thumb, the value of knowing the mean and the standard deviation of a population, is because you get an idea of how tall someone needs to be to sort of be significantly tall, or to be tall enough to be rare. Because the thing that we want to remind ourselves is the ones that are not significant is about 95% of the data is in there. So to be in the significant extremes, there's only 5% of the data that's small enough to be that low or big enough to be that high. So you're kind of usually thinking that there's maybe 2.5% of the data that's significantly high and 2.5% of the data that's significantly low. Man, we are almost out of time already. This is tough stuff. So I'm gonna, in a couple of minutes, I'm gonna quit the slides so I can at least go over and give you one example of how to avoid all these formulas and do the calculations for the data in StatCrunch. What do they talk about next? Simple range rule for estimating a standard deviation would be to take the range that we talked about in the beginning, the difference between max and min value, and divide by 4. This is very rough. We're not going to really use this much in this class. You may have a problem asking you to do it. So the range rule of thumb for an estimation of standard deviation is just take the difference between the max and the min and divide by 4. So another formula, now they're talking about the population. So the last thing I want to do in these slides is introduce the concept of variance, because variance is almost the same as standard deviation. If you look at this, it's just the square of the standard deviation. And so why do we need to have another word just to take a square of something we're already talking about? That's a long story, and it may become more clear to you by the end of the semester, but it's not that important. Initially, just remember what the variance is, that if you take the standard deviation and square it, you get the variance. Now, the one thing to point out in terms of some of your problems when we get to that is that because the variance is the square of the standard deviation, that means that the units are squared as well. So if I went up to my standard deviation here, where my standard deviation was 4 inches, then variance, without even caring about what it is or why they have that, would be 16 square inches. Because when you square inches, you get square inches, if that makes sense. Just as a unit, because some of the questions I think will ask you that. All right, so we're down to about 5 minutes left. So any questions at all while I got the slides here before we hop over and take a look at how to do these calculations in StatCrunch?
Yes, I have a question. So in this example that you gave, the sample standard deviation is 4 inches. How did you get that value, and can it change for different data sets and studies?
Absolutely, because it's that crazy formula, which I said we're not going to use. That's why I just gave it, because I didn't want to talk about how to get it. But what I've been saying is when we have data, we won't do it ourselves. We will use a calculator to do that for us. And that's what I'm going to show you next.
Okay, thank you.
So what we're talking about here is what it is and what it means and what it tells us about the data. And I'm trying my best to ignore the calculation you go through to get it, because that just makes things even worse. Does that satisfy your question?
Yes, thank you.
Okay, so let's got 5 minutes. All right, that's enough. So let's keep recording while I hop over and look at figuring out these data values within the assignment. So I'm going to go over to number 3. And I think I scoped out 22. Yeah, 22 would be a good one to look at. So this is, as usual, a homework problem from the current homework assignment, or at least from chapter 3. This is specifically 22 on the homework problem list. And so it says listed below are the amounts, and the units are dollars, in costs for marriage proposal packages at different baseball stadiums. And then it just says find a bunch of stuff: range, variance, standard deviation. And those are all sort of measures of variance that we were discussing in 3.2. All right, so as we saw, well, the range, we could just take the difference between the biggest and the smallest. And they did nicely organize the data for us a little bit, because it looks pretty clear they're organized from smallest to biggest. So let's say we took it upon ourselves not to immediately jump into StatCrunch, because we can do that. So what would the range be? Well, then it would be the difference between the biggest value and the smallest value. So 2,500 minus 39 is something like 2461. Then it asks us also to say what the units are. So they've got a box here for us to select what the units might be. So anybody have a suggestion for what the units would be?
Wouldn't it be dollars?
It would, sir, yes. So since we took a difference between $2,500 and $39, the difference is dollars minus dollars is just a gap in dollars.
All right, cool.
So that's to be clear, the data values themselves have a units of dollars. And one of the things we looked at with range is that the unit of range will match the units of the data. So let's see if they agree. They do. So then it wants standard deviation. That was the crazy formula. So I don't want to touch that myself. I want StatCrunch to come to the rescue here. So let's see if we can do that. So I did also illustrate this when I was going over 3.1 earlier. And so I'll try to reiterate it a little bit here. So far, we've been using the graph tab because in chapter 2, we did a bunch of graphs. But what we're doing now is we're going to use the other tab, stat. And these two tabs are basically going to cover us for the whole semester. And stat, things like mean, median, mode, standard deviation, range, variance, those are all examples of what we call summary stats, which is this second thing here. And in this case, our data is listed in column 1. I'm just going to go to columns. As we saw, even when we're making a histogram, you pick the column that you want to focus on. And then for this tool, they just have this list for us of all these different things. And they have some of them pre-selected already. So you might be able to compute and just get what you want. But you can also pick from the list. Like I know I want standard deviation. And if I click on it, then it just moves that over into the selected column. If I click on the control button, then I can add things to here. If I click on something else, it'll replace the one that I had there. But if I want variance, which is one of the things they asked for, but I also want standard deviation, I'm going to hit control standard deviation. And then they wanted range, which we already did, but I'll just show you we could have had this do that for us. And I think that's what they wanted. And then I'll hit compute. And so they'll give the values here. Notice there are no units here, so you're going to have to follow through our discussion about units. But that's how you can get the things that they ask specifically, standard deviation and the square of that, which is the variance. They can be done in StatCrunch by putting the data over there. And it is now 1:45. So I will stop my description there. I'll leave this if people want to follow up with questions, but the class is over. So let me go ahead and stop the recording.